Assalamualaikum and good day everyone. Now we're going to continue our week 12 lecture. Okay. Last time, okay, let we refresh what we have learned before. Okay. Last time we learned about the transformer EMF. Okay. Where we learn actually in that stage, what is actually happening in that situation is that we have a set stationary loop, but we have a changing of B field, okay, with respect to time. So we learned about this equation: VMF equals to closed integral of EDL equals to negative dB over dt. Okay, because it's a time varying. So in Sadiku is the page 428. Okay. Now we're going to learn about the motional EMF. Okay, and transformer plus motional EMF. This one is like a hybrid case because it's combination of both. And motional EMF, what is the word motional? Means some movement is involved. Okay. So we continue. So you guys may refer the motional EMF from the page 430, okay, and so on. Okay, so I will be explaining in combination with the slides and also Sadiku books. Okay, and if you notice there is if there is any conflicting information, please let me know. Okay, if there is like conflicting between the Sadiku books or with my teaching or with the lecture video, okay, anything, if you find there is conflicting information, feel free to let me know. Okay, so now we continue with our week 12, okay, lecture about we're going to cover hopefully on motional EMF and also the hybrid case. Okay, so now, okay, just want to take note is 6th June, okay, 2021, and it's 2:52 a.m. Okay, so I just want to see. I try to stop this less than 1 hour because otherwise my phone will have storage memory problems. Okay, so let me start. Okay, what we actually have. Okay, please refer to your slide as well. Okay, your slide. Okay, and in the book also, Sadiku book. So what happened? Okay, let me see on the motional EMF here. What is actually happening in this motional EMF? Our B is constant. Okay, but we're going to have a moving circuit. Okay, our circuit is moving now. Moving circuit. Okay. Okay, so then we if you learn from your transformer EMF, okay, in your transformer EMF, what is actually happen in transformer EMF is that your B is now varying. Okay, in your I just want to recap, and then what is your circuit? Circuit is static. Okay, your circuit is static. Okay, so if in your transformer EMF it is V EMF equals to, I don't want to discuss further, you may see from the previous lecture. I just want to show you the the relations. Okay, Okay, this one is what you have learned, okay, from your previous lecture. Okay, so now we want to learn about what actually happened in your motional EMF. Okay, so there is some movement involved already in the motional EMF. Okay, so imagine that you have a loop. Okay, when you have a conducting loop is moving in a static B field. Okay, so imagine, I mean, you can see from the even the simplest case. Okay, for example, let's say you have this. Okay, you have this an area where you have the B passing through. Okay, you have the B passing through. Okay, you guys also can see example from figure 9.6. Okay, it just explain the same thing, not the same, but the situation. Then you have a rod here. Let's say you have a rod here. Okay, then this is your B field. So what happened is that you're going to encounter that rod will move at a certain speed. Okay, and then you will have, when you have you will also have what? You have a magnetic force, Fm. Okay, we can put Fm. Of course, it is a vector. Okay, so this is a magnetic force. Then if we were to take this one out, okay, this rod you put here, okay, you zoom in the rod, okay, then you can see that you have your B here, okay, here. Then you have your u, the velocity, the spin, okay. Then you have your Fm, the movement, okay, the movement. Magnetic force involved. Okay, and you see this is a rod, right? So it have its own, let's say we want to represent like what we refer in the previous case of electrostatic, we normally choose rho v, because inside rho v is a general to represent for surface, for line integral, for line charge. Okay, so we have this is your rho v. Okay, and then you have your dq. Okay, you have your dq. How you check? If you sample, you have your dq. How you know this is sample? Then you have rho v dv, right? This one is what you learned. Then q is actually rho v dv. Am I correct? Okay. Okay. Then we learn that we have in electric and magnetic, we both have force. Okay, we have magnetic force and we have a electric force. Okay, so what we have learned in the previous lecture, we have learned about electric force, right? Okay, now we are about to learn, or we already maybe you already start to encounter a magnetic force. Okay, so they are analogous. Okay, I think you there is table. Please refer to Sadiku where they show is the analogy between the electrostatic, magnetostatic. Okay, and also you can see now in this EMT, I mean in this chapter already we combine both. Okay, so in the magnetic force, okay, let's say we take a differential for a small force, okay, sample, okay, it is based on charge. Okay, oh sorry, it should be here. I'm sorry, because we're discussing about charge. If it's about charge, it's the electric. Okay, so df, where we have our sample charge. Okay, Then what we have after? We have electric field intensity, where is your E. Okay, electric field intensity. Okay, so when you actually try to expand, then you have this, right? Am I correct? Okay, later we will integrate in order to have the total force. How about in the magnetic field? Similarly, we also have a dF. Okay, but now it is with respect to the magnetic field intensity and also with current. Okay, so you have your sample current. Just like here, we sample charge, okay, dq. Okay, we use volume. Here also sample current, we will also use the volume. Okay, then we have, now here is dot product. Okay, dot, then here is our cross for magnetic field. Okay, do you see this is a sample current? Okay, so what we have learned from the previous lecture, okay, let me try to find our related formula just to show you that we already covered. Okay. Sorry, you may find from the previous lecture. Okay, yes, finally I find it. Okay, so in the previous lecture of magnetostatic field, okay, 27th of April, where I called it, you see we JdV. Okay, JdV. So this is actually the sample current. Okay, and that's why here you can use JdV. Okay, time with your magnetic field intensity. What is it? It is P. Okay, then you also learn actually this J can be described in many ways. Okay, in many ways. Okay, so this J here, let's say your rho V and your U. Okay, if you see this is JdV. Okay, this is your dq. Dq can be used from here. Okay, and this JdV for the force for this rho V and U with cross of your B. Okay, and you see rho V dV is actually equals to Q. So you see here, right? So if you see, sorry, this here is a rho V dQ. So it can be your dq rho v, sorry, is a bit wrong, okay, df, okay, and then if you to consider j dv and rho v, okay, and you know that j is can be rho v mu, okay, here I just put aside here rho v mu, and here is your dv, okay, here is dv, j I am sorry, a bit the confusion, okay, because it's late night, okay, sorry, so j dv, okay, you know that j is equals to rho v u, okay, then dv here, then you further df equals to j rho v u dv b, okay, then we rearrange, okay, you can see dq is equals to rho v dv, okay, so it's dq rho v dv and u b, then you obtain your df, okay, then here you obtain your force, okay, force for electric, and this you obtain the force for your magnetic, okay, magnetic force. Sorry for that, just now a bit confusion on my side, I'm sorry, okay, and then if you see is the relation between E and UB, okay, if you were to compare this equation and this equation, you will see that there is a bit of similarity there, df dq, and you can see this one, okay, so you can see that E is mu is u cross b, okay, now we go for what is being this we want to discuss further, okay, so this is when we see this is a motional electric field, okay, okay, for the motional EMF, okay, from equation 9.10, if you see from the Sadiku book, so we introduce, okay, VEMF equals to closed integral EM dot dl equals to closed integral of L, okay, this one is also L, U cross B dl, okay. If you see here, U and B, there are sometimes there are cases where they are perpendicular, just like in our example, and also in our equation of in our figure 9.6, okay, where U and B is perpendicular to each other. If you can see, this one is going here and B is going in, okay, this one is in, sorry, this one is going in, so U is here, so they are perpendicular. So we the equation, okay, the equation can be varied, okay, can be varied to because in some case where they are perpendicular, in the case of B, perpendicular with U, okay, you can have Fm equals to I L cross B, okay. Of course, this is a vector, okay. This one also a vector, okay. Okay, so far so good. You can see, right? Okay, I think you also can see from the Sadiko book, okay, the equation that I'm discussing is actually from 8.2, okay, Sadiko is 8.2 until 9.11, okay, equation involved, okay. If we to apply Stokes theorem, okay, what we actually learn from Stokes theorem is actually line integral change to surface integral, right? So if you see this is both line integral. So if we want to apply Stokes theorem, okay, if you want to apply Stokes theorem to here, okay, then we will have, okay, for this one, okay, I just rewrite again the equation. Before I'm changing them, okay. So if you want to apply the Stokes theorem where we want to change to surface integral, okay, so then we will have surface integral, okay. Now we have surface, then we have curl of EM, okay, you see EM, and this one ds, okay, and surface integral, and this one is what? This one is another curl, okay, another curl which inside here, okay, curl of curl, okay, then dl we have a ds, okay. So it's depend, okay, here is the surface integral, here is your line integral. So if you want, if you see, if we take the common, okay, we remove the common and we only take the one that is different, we will actually come across, okay, this, okay, because you see this and this are the same, so that's why we have here, okay, sorry, okay, okay. So you guys can see the examples, okay, the examples on figure, there is, okay, so there is also noted of points, okay, to apply equation 9.10, okay, it's not always easy. It says some K must be exercised. The following points should be noted. So what is equation 9.10? This, okay, we not always easy to use, okay. So let me see what they say. The integral equation E is 0 along the portion of the loop where U is equals to 0, okay. Thus dl is taken along the portion of the loop that is cutting the line along the rod in figure 9.6 where U has a non-zero value. dl is taken along the portion of the loop that is cutting the field, okay. So which actually of the movement actually cutting the field, okay, cutting the B field, okay. So I think this one you will see later on. I think there is also explained here, okay. If you see the movement, okay, if you see the movement from here to here, and if you see your B, okay, you see your I, okay, so it is actually like this, okay, your B. So the one that cutting is actually the one that having the movement from left to right. How about the one here? It doesn't, okay, it doesn't cut, any field. Okay, the one that's cutting is only this side, left, right, and top and bottom doesn't cut anything. Okay, doesn't cut any field. Okay, that's why it mentioned here. Okay, is the integral is 0 of the loop where u is equals to 0. Okay, thus dl is taken along the portion of loop that is cutting the field. Okay, dl is only getting the value of dl is only taken for the one that cutting the field. The one that doesn't cut, we don't take it. Okay, it's what I discussed just now. The direction of the induced current now is the induced, okay, not the current. The induced current is the same as that of EM or U cross B. Okay, the direction of the induced current, okay, the direction of the I induced, okay, let me see here how the direction is actually the same. Okay, this one is not equation, okay, just want to show you it is the same. Okay, it is the same with the direction of mu cross B. Okay, this is not equation, it's just to show that this induced direction is equal to the direction of u cross B. Okay, the limit of the integral in equation 9.10 are selected in the direction opposite to the induced current. Okay, remember, the limit of the integration are selected in the direction opposite to the induced current. Okay, thereby satisfy Lenz's law. In figure 9.6, the example of the integration over L is along negative AY. Okay, you see here, figure 9.6, this is the current along negative Y, and you see the induced is actually in positive Y. Okay, they are opposite. Okay, this is the I, this is the I induced. Okay, the integration over L is along negative AY, where induced current flow in the rod along AY. Okay, the limit of the selected in the direction opposite to the induced current, opposite to induced current. Okay, because the induced current is in Y direction, opposite, so negative. Okay, so that's why if you see in this case, okay, I just want to explain. Okay, if you see from this case, reward example 9.1, which everything the same except that the current I, where is example 9.1? Here, okay, with everything the same except that the current I changed to I 5 ampere. Okay, and the rectangular conducting loop now is moving. Okay, constant u, constant velocity u in y direction. You see, is y vector. Okay, so now they are moving in this direction. If you see your I and you see your, this is the resultant field. Okay, okay, circulating in y direction. So what actually cutting the field is actually this one and this one, right? Let me do some just like a one. Okay, what is the one that cutting the field when it's moving? Is only this one and this one, left, right. How about the top and bottom? They don't cut anything. Okay, because they are actually almost like in the same direction of y. Okay, this one, they are cutting now because we have, you see, we have a lot of, okay, we have a lot of field, and this one is at this level. We have a lot of this according to this along the current. Okay, so the one that cutting is only left and right. That's why in this equation, if you see, for this equation, you can see, right, they use the VMF U cross B DL. Okay, and DL is actually taken from the one that actually cutting the field. First, you put all the possible combination, left, top, right, and bottom. However, then like what like the book said, and I also explained, the one that actually cutting the field is actually left and right. So this one can be 0, and this one top and bottom is 0. Okay, so as determined using Appear's circuital law. Okay, never mind, this one you can read later on. And you see, that's why the VMF the resultant that actually is left and right only. Okay. So how about the hybrid case? Okay, the hybrid case is actually they are combination. So nothing new about this hybrid case. Hybrid case is just a combination. Okay, hybrid case is combination. So combinations of if VMF for hybrid case is V transformer EMF plus V motional EMF. Okay, so what is question for the VMF for transformer? Okay, we example. Okay, the question, sorry. So it's actually this transformer, your surface integral dB over dt, because in transformer the changes is the one that changes the field, that's why over time dt, and your ds. Okay, and negative, you see here there is a negative. Later I put some highlights so that you guys can see. Okay, and then contribute by your motional EMF now, which is we can have closed integral of u cross b dl. Okay, so this is just a combination. Okay, combinations of transformer and motional. And from equation, if you see from equation 9.8 and equation 9.14 from Sadiku, okay, so you will get to know about this. Okay, you may refer from the Sadiku for detail. I will just summarizing. Sorry for the noise. Okay, if you listen there is background noise, I'm sorry for that. Okay, okay, so you happen to also see this equation. Okay, okay, please look into the supplementary video. Okay, supplementary lecture video. I might not have the time, I might forget to put at e-learning. Okay, supplementary material. Okay, the EMT education. Okay, education, week 12. Okay, week 12. Lecture 11. Okay, lecture 11. So here he discussed, the professor discussed very extensively about all the things. Transformer EMF, motional EMF, and also he discussed about the tutorial as well, tutorial 10, which is on Faraday laws. Okay, okay, so this is the what we learned today for the motional EMF and also the hybrid case. Okay, maybe I will. Okay, you guys can see now. Let me just to put something. I think I a bit sorry, let we take some space here. Okay, so for example, let's say in case, I think you a bit familiar with, let's say, dynamo or something that moving, right? Dynamo, do you guys know dynamo? Okay, so let's say we have this is just want to set to explain to you the one that cutting the field is actually contribute to contribute, but the one that doesn't cut, it is 0 actually. So here, okay, you guys can listen from here, this lecture, okay, he explained in detail in motion EMF, he explained in detail about this case, okay. Okay, so here you have your B, okay, your B field, okay, then you have the sides, okay, the side 1, 2, 3, and 4, okay. In the case actually which one actually cutting the field, that one is actually the one that contribute for your VMF. This one is moving, okay, they are moving in mu speed, in omega speed, okay. So omega is also 2 pi f, okay, it is a radian per second, okay. So you see this one, which one is actually cutting the field? You can see when this one is moving, okay, when this one is moving in this direction, maybe I should put in red color so that it is more clear, okay. So which one is actually cutting the field? Is 1, 2, 3, or 4? Okay, if you see and you try to imagine, the one that actually cutting the field is actually B. Actually the side 1 and side 1 and side 3, side 2 and 4 didn't cut. That's why similarly VMF is V EMF 1 plus V EMF 2 plus V EMF 3 plus V EMF 4, okay. That's why in this case, okay, the one that actually cutting the field is counted, okay, because the one that didn't count, they didn't cut the field, they didn't contribute to anything. So that's why 2 and 4 is 0, okay. You only count the side 1 and side 3. So please watch this lecture video, okay, in case I didn't include the link in the e-learning, okay. Now to shorten the time and to save my memory, so I do the exercise in advance, okay, to help, okay, to speed up the learning and recording to save my memory. So we go to practice exercise 9.1, okay. Consider the loop of figure 9.6, okay. Now I redraw them. This is figure 9.6. If B is equal to 0.5 in Z direction and R is equal, given 20 ohm, and L is 10 centimeter, and U is equal to 8x in X direction, okay. If you see this, you see the similar diagram, just similar figure, right? Your I is going here and your induced I is going opposite direction. B in is, because you can see from here, is going in, and this is the resultant velocity and magnetic force, okay. This is your axis X, Y, okay. So the question is asking the induced EMF in the rod, means it is asking for VEMF, okay. So this one is involving movement, so this one is a motional EMF. So we just use this VMF, U cross B DL, okay. And you see what is the resultant of U cross B? You get a vector, right? X cross Z, and then dot with your DL, okay. Then you have UBL, okay, because this one is just the resultant of VMF is just a scalar, so we don't need direction, so it's UBL without the vector. So 8 times 0.5 times 10 to power 10 or 10 negative 2. 8 coming from your U, B coming from your here, and this one is 10 centimeter. This is why 10 to power 10 times 10 to power negative 2, you get 0.4 volt. The next question is asking the current through the resistor. You know from the general equation, you have V equals to IR. So I equals to V EMF over R. Okay. So you have 0.4 over 20 ohm. Okay, you get 20 milliampere. Okay. And then from the motional force on the rod, you learn just now is what I shown. Okay, F can be ILB. Where is it just now? Here, F IL cross B. Okay, so F equals to ILB. Okay, then this is the general. Then involving the specific one is F equals to IL cross B. Okay, of course this one is all having all having vector. Okay, all are the vectors. Then 20 milliampere. Okay, this one is given. Okay, and not given, we obtain 20 milliampere. And then L we know is 10 centimeter, and then times 0.5 times 0.5 is given. And now we need to see the direction. You see, if you see why it is negative y for this I, because if you see, wait for what, something something at my eyes. Okay, where were we just now? Okay, negative y cross of z. Okay, cross of z. So B is actually in the z going inside. Okay, so the result you can calculate your own. Okay, and after that